for the invitation. It's a great pleasure to be here. This is my first time. I enjoy very much. I also would like to thank the organizers and the helpers for that royal treatment we have been so far. So my topic is numerical methods for SDEs, and before starting the method, I should give a brief summary of the results of SPDEs in one approach, the L2 approach. In fact, these will be already explained partly, but will be explained in the lecture by Professor Kulov, so I will not prove, I will give a summary. But first the motivation. So the motivation for me as well as a former student of Kulov, the nonlinear filtering equation is the main motivation. And as it was proved for him in the special case, when the observation is a linear process, and the general case can be treated as well, first by the Gibbs-Arnold theorem in order to transform the observation process into the situation of a linear process. So then, as he explained, one gets an equation for the density, or more precisely for the unnormalized density, and that looks like this. Plus and here the observation, usually I denote it by yk, but that was denoted just by w, linear process. So here we have a multidimensional linear process. When I write k in product wise, that means the summation with respect to that index, if I'm not state otherwise. So here W is a multidimensional linear process in the multidimensional case, MK is a first order differential operator, and L is a second order differential operator. So and we have an initial condition. Let me write L. In general, is of this form. And here, my notation is that there is a summation with respect to alpha and beta, where the d alpha means the derivation in the direction of the i's coordinate. If alpha is I, alpha can be also 0, so just for short notation, that means the identity. A is a function which depends on t or a alpha beta, which depends on t, omega, and x. X is, in my case, is always on the whole space, so I don't consider the Van case, so the space is x Rd. So here u depends on t, on omega. I didn't write the x, but it depends also. As I have already told, the coefficients a, so alpha then runs from 0 to d in this notation, and mk for each k is d alpha k d alpha and also b alpha k depends on t, omega, and x in the case of the general filtering equation, or so-called Sakai equation. Right, I think I explained everything, how it looks like. And so now, in order to, so the motivation is to get numerical solutions for this equation as accurate as we can. And what I will consider is several approaches, finite differences, so finite difference scheme, splitting up method, and finally I will consider also the Von-Sakai approximation and extrapolation methods to get the accuracy better. But for all these methods, first one should have a good theory about the equation. So let us see this, for example, why we need that. We will use a very simple approach, and the calculations look a bit complicated, but in fact not. So let us consider what is this method consist of. So for example, if we just instead of L and MK, we take finite difference operators, so that means the derivatives are substituted by finite differences, then we substitute that equation by the finite difference equation. I am doing it just in X now. And then we want to compare U and UH. Then the obvious thing to do is that one writes down an equation for the difference UH minus U. And that one can write down like this: LH UH minus U, obviously plus LH minus L on U, right? And we have also the similar writing for the stochastic terms, so MKH on UH minus U plus MK on U MK minus MKH on U So then we can view now this equation as an equation for this UH minus U with three terms. So here the dt. Sorry, please tell me always, if possible, when I make the mistakes. LH about LHUH, thank you. Then one looks at this as a free term for this equation, all together obvious here and here as another free term. Okay. for the stochastic part. And once one had, so then we can see what we need is that on the solution of the original equation, we should see that this term is small. So the free terms are small, similarly this one. So for this, normally one should have good regularity property from the solution. So therefore, one thing what we need to have is solvability and regularity properties about the original equation. And for the equation, this is the same kind of equation as the approximation, right? So for that equation, we need solvability plus estimates, good estimates independent of h, in terms of the free terms plus the initial condition. So this is a very straightforward approach. One could change this, of course, that instead of writing down the difference as satisfying an equation with LH and MKH, one can write down in the other way around that with L, with the original operator, and that is also used, but this is the simple main approach we will use, and then we will see what kind of results can be obtained. By the way, I should mention here the dissertation of Hayek Yu. It's a spelling correct? Sure. All right. So I learned a lot from this dissertation concerning the finite difference method, and this approach influenced me. And then later we will see what was said. Okay. So our task is then to write down the corresponding results which we need for the original equation in order to get the regularity property, and then later on the solvability of for example, the finite difference equation is easy, in fact, because these are for each h we have bounded operators on the right places which we are using, but one should also get estimates independent of h. That is the difficult part there. Right, so as Carol mentioned, it is better to have results when we have it's better to have to study the case when we have the free terms as well. So here Ft stochastic processes always adapted to the equation, and Gt is K added. And so this is the equation we consider now. So I formulate the basic result we will use.
Could you write a little larger, correct?
The back, yes. And also my handwriting should be better, but I'm afraid I can't change that. I understand. So the assumptions. So first assumption about the coefficients. So the first, the simplest case that is we assume to be bounded. So A alpha beta are bounded. Also B alpha K. Oh, sorry, I used C for the constant, and K will be a process later in notes, so it's better not to. Right, and obvious measurability properties in T, omega, and X. So such that the stochastic intervals in the definition of the solution, which I haven't done yet, but that is exactly the same what Professor Gyongy explained today. So the natural measurability properties plus boundedness from the free term that the F is a process in L2, is values in L2, or in fact it can be better. So maybe I consider once again this equation. I write it down in a little bit more convenient form. Is the E alpha beta, and then ut plus f alpha. So one can have f, and the derivative can be on f alpha as well. So let us forget that situation, the t plus the b alpha k ut plus g gk So this is our equation, and then for the free term, then we have f alpha and g alpha k are adaptive L2 valued processes. Yes, these are functions of t, omega t and x, and looking at considering it as a function with values in functional space, we want them to be L2 valued adaptive processes. Sorry? G, K, there is no alpha, right? Thank you. And the n-square integrable. So from 0 to t, f alpha squared in L2 norm. I write just 0 for the L2 norm dt plus g. Is finite. Should I have this second, and then the third one is that u0, the initial condition, initial value is almost surely in L2, and the f0 measurable. Right? The notion of the solution, let me repeat, now it will be a longer formula than we have seen today. That definition.
Do you need some small L2 condition for D alpha?
Sorry?
Okay, you use from the summation.
Yes, you meant, so this should be, this is asked for each alpha 0, 1, 2 and d, and for each k. For simplicity, let us take finite dimensional linear process, but one can consider the little L2 value keys as well. But in the nonlinear filtering equation, one normally has a finite dimensional case, so we consider now that one, and here as well. So the definition, so we say that that ut, that a continuous L2 value process is a solution. Continuous L2 value adaptive process ut is a solution or generalized solution, in other words, of that equation, if almost surely ut is in H1, which I use H1, this notation. I think that today this was used 1, 2. I usually forget the 2, and that means the same. So this is the W1, 2 space on the whole RT. Yes, that L2 functions with L2 derivatives. Almost surely for almost every t from 0 t, and so this is one thing. Second, that it is in the L2 space in time, so the ut H1 norm, which I just write 1 here, so that means the H1 norm integrated is finite, almost surely, and the equation is satisfied so this equation is satisfied by using test functions, that is for every phi from C0 infinity, the inner product of ut with phi is u naught inner product phi plus the integral from 0 to t and d alpha a alpha beta us plus f alpha s. Oops, sorry. I'm writing. I wanted to do the integration by parts. So here, this the d alpha star, the d. Oops, sorry. Thank you. D beta.
In the equation too.
And then that as well. And d alpha star on phi ds plus from 0 to t d alpha k d alpha us phi. Oops, here I lost the g. Phi d w k s. So this holds. So for every phi, almost surely, for each, for all t in 0 capital T. This means this is just a notation for minus di when alpha is I, and the identity when when alpha equals 0. So the natural notation dropping the natural definition dropping the derivative onto the test function. Here one can also, if one wants to get this, almost surely it is equivalent if we ask almost surely that this satisfied for all t and all phi. Or equivalently, we can also ask here, instead of all test functions, all phi from H1. That is an equivalent requirement. Okay, now what is then the main result? That, so theorem 1, that if I write also the main assumption, which is now 4, that the stochastic parabolicity is satisfied, which we have seen this morning. So in this multidimensional case, one can formulate like this, that the Aij minus 1/2 and then Bijk Bjk, this matrix, so here this is in I and J, so let me write that down like this, Zi, Zj, this is greater than or equal to lambda times the sum of the Zi squared for all Z from RB, and almost surely for almost every t, for all x that should satisfy, for all and all z. So this is the electricity condition of which we have seen this morning, but that was the one-dimensional case. In the multi-dimensional case, this is how it looks like. And as we have seen, this is a necessary condition to have solvability. One can, here lambda is a fixed positive constant. It can be 0 as well. So I should have started here that there exists a constant lambda which is positive, such that this is satisfied for almost every omega t for all t for all x and z. So if these conditions hold, then there exists a unique solution. Okay, moreover, one not only the existence is needed, but also estimate in terms of the free terms and initial condition. So here I haven't assumed finiteness of the expectations. So therefore, the estimates are given weighted in the time. I use some weights in order to give the estimate. So suppose so that nu t positive or non-negative adaptive process. This is our weight such that the expectation of the initial condition norm squared times e to the minus mu norm is finite, and the expectation of this, let us denote this is a process of a of t. Here this is in fact at capital T, but obviously you can define it for t more than capital T. So we also want that the integral from 0 to t of k t multiplied by say e minus mu t expectation is final. So let us take such a weight function. We can always find such a weight function, right? Because we can.
What is the k there?
Sorry?
What is the k there?
This k here.
Oh, that,
This is the function
oh, that,
of from this parenthesis point. So okay, we can always then find. So for example, take mu t equals the initial condition norm squared plus the kt function. Then one can easily check that these are satisfied. Yes, because the u naught multiplied by the minus u naught norm or squared and squared there, this is always less than or equal than some constant, if I remember well, by e, and this and easy to see that the integral of this is less than 1. So, simple exercise, since one can see that the e to the minus mu t, if one define mu t as it is defined, has the differential minus kt times e to the minus mu t dt. So, from here, one can immediately see, right, that the e to the minus mu t equals 1 minus integral from 0 to t ks times e to the minus mu s ds. So we can, this is non-negative, so from
So
here
should there be a derivative of k?
Sorry?
Should there be a derivative of kt?
No. So here the
Mu t is this.
mu t, sorry, mu t,
Yeah.
oops, right. Yeah, thank you. This is what I wanted. And now this is the right. So we have this way, and then in the term, then we have that there exists a constant. Moreover, there is a constant mu depending only on the dimension, the lambda and the constant c, such that for all mu which is bigger than or equal to mu naught, this estimate holds. So the supremum minus mu t plus the expectation integral from 0 to t e to the minus nu t minus nu t, and the solution is denoted, so this is u t 1 squared dt is less than or equal than the constant c times the initial condition multiplied by the weight expectation as well. Plus the c times expectation integral from 0 to e to the minus nu times t, and then k dt, where c depends only on lambda dimension and on the capital C, the bounds of the coefficients. Right. So
Supremum is the
sorry?
the first term.
The left side, the supremum of
Supremum. I lost the. Sorry. And this is squared and
should there be a t after nu?
and so expectation. So with the weight multiplied and the supremum is outside. Now how to prove it? So I will not, because we learned the idea from the continuation of the lecture, but just that there can be various approaches. So one standard approach to prove this is the Galerkin method, that one takes a basis in the H in the L2 space, such that those are from elements of W of H1 space, and then one takes finite dimensional projection of the equation, then a stochastic differential system of stochastic differential equations is considered, and using the coercivity assumption, one can get an estimate for the solution of the system, which then is enough that one can take weak limit in the system to get the equation.
T is missing after
First one.
supremum of
Supremum
Nu t
ut.
on top.
Exponential
Differential of the nu
This is
Yeah.
U and then U T.
Yeah.
nu t
Ut minus. Nu need to multiply by
t.
No, that is how.
Should be sure.
Yeah, I think I have written properly. So here, this is the weight function, appears as a multiplier, and the supremum is taken.
Yeah, if you look at the other terms,
Yeah,
you
nu
all
t.
have nu e negative nu t minus nu t.
Oh, here. Okay, you're right. Sorry, that is really missing. Yeah.
Minus
and the crucial role in having the uniqueness, and also, so more precisely, the way is that first one proves in one approach, for example, by the Dworkin approach, a solution in the weaker sense, which satisfies the equation in the weaker sense. That means that such a one gets a function which is W1 valued, no continuity property, and this relation is satisfied for each phi for almost every t and omega. And then one, by using Ito's formula, which we will see later, but I formulate it now, one can get that once we have such a solution which satisfies in the weaker sense, and also W and H1 value satisfying this integrability condition plus the equation in a weaker sense. Once we have that from here one can see that exists. So an L2 valued continuous modification. This is what Ito's lemma will give us, which I formulate here because we will need that lemma as well. And then and in this way we get the solution in the stronger sense, how it is defined here. So let me formulate then the basic tool, which is Ito's lemma, which we will then see the proof, but not by me. Oops, no, maybe I should have. This one. So the crucial role in this L2 approach is played by Ito's lemma and the square, which is known also, the deterministic version is well known also, this one is as well, I suppose already, so Ito's lemma. So consider processes dt, then f alpha, let me use my notations, and h k. So let these be L2 valued and predictable processes, and assume that again alpha runs through 0, 1, 2 and so on d, similarly as before k is 1 to d1, and assume that that d alpha v is in L2 and its L2 norm squared is integrable and also that the integral of f alpha L2 norm squared and dt is finite until capital T. Let us consider everything until capital T, or more generally, one can consider it until a fixed stopping time tau. And that the integral from 0 to t g of h, that is h I h j inner product, and oops, why do I do this? I wanted to, sorry, not inner product, just take the, in this special case, just take the hi L2 norm squared sum over I dt, that all these are finite almost surely. So one condition, second condition, that for every fine C0 infinity, we have a similar relation as it was written here in the definition of the solution. So that means that Vt phi inner product in L2, when I use this one, that means always L2 product equals V naught phi plus integral from 0 to t, the f alpha s and d alpha star, the star notation of phi, ds plus integral from 0 to t, and h k phi d w k s. That for each phi, this equation holds. So in other words, that the V process has such a differential as is defined here for every phi, but that we want that this should hold for dt cross or t cross dt almost everywhere. And so more precisely, almost that for almost surely this holds for almost every t with respect to the dt measure, which is less than the tau on omega. So for almost every omega, for almost every t less than the tau omega, one has this satisfied for each phi. Then there exists an FT adapted continuous function, continuous process, and that is denoted here by, that was denoted by u, and there exists u continuous FT adaptive such that for almost every omega, and even one can ask that for every omega, if one wish, that this stars holds for all t less than tau, and for all phi. And moreover, Ito's formula for the square holds, and that is the assumption. Moreover, the square of ut, the norm in H in L2 equals to what we expect, that is the B naught, U naught square plus twice interval from 0 to t, and S and D of star US and S plus the interval from 0 to t to H I S US EWIS plus the quadratic variation H I square 0 ds over I, and I haven't said that continuous F, the adaptive L2 value, which is important, L2 value. So we started with an H1 valued process according to this one, but it doesn't have any time regularity. But because there is such a requirement for the differential, now that is only for dt, so p cos dt almost everywhere. But from these two, one can get a continuous version, but that is with values in H, which satisfies the Ito formula. So this is the crucial lemma, crucial theorem to get the existence and uniqueness theorem, or decided the uniqueness theorem, and one can prove existence, but not of this sort, but the weaker sort of solution without using this lemma. But using this one, then one gets the continuous modification of that, so then one can get a solution, and also one gets this estimate. So I
So
think
is your H1 value?
So,
Is your H1 value?
no,
Because you have these
Just go.
yeah, but that's a very good question. But don't forget that it turns out that by this that it takes values for almost every omega and s in H1, because here we require that. And so then though one needs to say some words here that this is well defined, but this is well defined. This will also. Okay. So, right. So this is how one can get and this is what we will use, though in the abstract version, so in not just this version of those formula, but one needs also regularity for the solution. Now, how to get regularity for the solution? So here we have 4 requirements that is kept. The stochastic parabolicity kept always, but now assume that we have that these coefficients are differentiable in x up to order m. Let's say so we fix m is an integer. And suppose that then up to order m, so this means all, okay, no, let me write it like this. So the partial derivative, here the alpha is not a good thing, gamma, all partial derivatives up to order m are bounded functions, bounded by a fixed constant, similarly for the other. And here then, one requires that the hm norm, so the first that the free term is a process with values in hm, and the hm norm squared is integrable, here also with m. And so now if these are satisfied, then there exists, so again, but now with m, then there exists a unit solution. We have known that before, but also one knows that the solution is, so this u it is a continuous that this nu dominates. So let me write it down. Then here the m norm, hm norm should be also here the hm plus 1 norm, here the m norm, and then the kt is now with an m, where the m is where the ktm is defined from as the f sum f alpha m squared plus sum and k over k gk squared m. Sorry? I think that originally I defined the k without an integral and defined it after the, yes, without the integral, and that one gets here the its integral. Yes. So
you define the kt using the interval, but
that was a mistake. I'm sorry for that. So the k, in fact, without the here without the integral because if I write here the integral, sorry, here, then in the definition I should be right. And the proof of this is the bystander method from PDE. That is one, roughly speaking, one take the derivatives of the equations, and then one is at the same situation as in the case of the original equation, and one uses that result, the first result, and from there one gets the result. Okay.
Do you want to add condition state? Do you want to change condition state to that there is HN?
Condition 3.
And if there is the HN or...
Yeah, thank you. The condition 3 must be also change everything. Yeah. Sorry. This is in HN, and I suppose I have everything here. Yes, and it is here. And okay, the new weight function, the weight process is related to this one. It's integral, but with it is defined such that this is finite. So without this one, it is already finite. So this is how this is defined. Okay, so this will be used, this regularity. Now a slight, or maybe not so slight, generalization of this situation. When we have an equation with now not with in one case we will need that as well, that we have B alpha beta B oops, alpha is here, beta u plus f alpha, and with B nt, where nt is an increasing continuous at the adaptive process, and here generalization also to martingales. Where M is a finite dimensional continuous martingale, and the generalization goes roughly in the same way, so I don't want to take more time. I think that my time is... No, still I have. So we will use the generalization when we have here an increasing at the adaptive continuous process and a continuous martingale or local martingale, and then one should change the setting a bit. So let us assume, without loss of generality, that the anti-process in this case dominates the quadratic variation of the martingale. In that case, the only modification which one should require in the assumptions is that at the stochastic interval part, one should take into account the quadratic variation of the MT process. So then one can show that there exists Q T process Ij such that the principal that this one is predictable and it equals the dm I and j n and t. So in other words, that this can be written as the q times the dnt differential, or in other words, that one can show the existence of such a predictable process such that this one can be written as the interval from 0 to t, the qij s d and s, and then one should modify the requirement for d with this norm. So in that case, what will be is the one. Maybe the simplest is that one also knows that this is non-negative and that a matrix, a symmetric non-negative matrix, that exists its square root, and then instead of the b, one always should consider, let's say, the b, and let us here a tilde, b tilde, say, k alpha is defined as this k and b, this is kj and bj alpha. So is this new b, and similarly is the k with the g. Everything remains in the formulation. It's the same. Okay, something more now, that it is useful to have these results put into an abstract scheme, and I suppose, something like Oh, only one of them. Okay, then I won't be able during that. So, oops.
I felt that should be integrable against NT, right?
Yes, here the change is then, you're right, that in that case this should be integrable with respect to NT, and this one should be integrable with respect to NT as well, and then the notion of the solution, remains the same, but accordingly is the NT. And there is a version of Ito's formula with the increasing process NT as well, and then the same results can be obtained with this. There is an essential difference when the martingale and the increasing process have jumps. That's then that's a different. Okay, unfortunately I'm too slow, sleepy. So sorry for that. So I was not able to tell the abstract scheme, but I will use that during the methods and the formulation. Okay, so that was all, and thank you.